In the chaotic landscape of modern computing, order is not accidental, it is engineered. We are investigating the fundamental linear structures that dictate how systems remember the past and schedule the future. Stacks and queues.
Before writing a single line of code, we must define our relationship with time. Access policies are the rigorous rules that determine whether we prioritize the immediate urgency of the now or the fair sequentiality of the history.
Two dominant philosophies emerge. The stack follows the LIFO principle, last in, first out. It is selfish. It pauses everything to handle the most recent task, like hitting undo in a text editor. The queue follows FIFO, first in, first out. It is democratic. It ensures the oldest request, like a document sent to a shared printer, is served before the newest.
Think of a stack, not as a list, but as a physical pile of cafeteria trays. You cannot grab the bottom tray without destroying the pile. You can only interact with the top. In computing, this structure manages context. When a function calls another function, the system pushes the current state down and stacks the new task on top.
This architecture drives program execution. Conceptually, every function call pushes a stack frame to memory. However, in reality, modern compilers are aggressive. They often inline small functions or use CPU registers for simple leaf functions to avoid touching RAM. But for complex nested logic, the stack remains the ultimate tracker of execution history. While stacks handle depth, queues handle flow. The queue decouples the producer of data from the consumer. Imagine typing on a keyboard faster than the CPU can process. The keystrokes enter a buffer, a queue, ensuring that the letters HELLO are processed in that exact order, protecting the timeline of events.
Abstract logic is useless without physical implementation. We have two ways to store these structures. Contiguous arrays reserve a solid block of memory. Linked lists scatter data across the RAM, connecting them with pointers. While linked lists seem more flexible, they come with a hidden performance cost.
Here is the critical engineering insight. Modern CPUs are incredibly fast, but memory is slow. Arrays win because of spatial locality. When the CPU fetches one array element, it grabs the neighbors too. With a linked list, the CPU must hunt for random addresses, stalling the processor while it waits for data. Basic stacks and queues are just the beginning. To solve complex problems like network streaming and distributed task scheduling, we must evolve these primitive forms. How do you stream a movie indefinitely without infinite RAM? You use a circular buffer. We treat the linear array as a ring. Using the formula next equals I plus 1 modulo capacity, new data overwrites the space at the back as it is consumed at the front. It creates an illusion of infinite capacity using a fixed memory footprint. When we scale to the cloud, queues become message brokers. RabbitMQ is a smart router. It supports complex delivery patterns, but it is generally transient. Once a task is consumed, it is deleted. Apache Kafka, however, is a log. It writes messages to disk and keeps them there, allowing consumers to replay history days later. It is a queue that remembers.
Ultimately, system design boils down to these immutable pillars. If you need to manage nested context, use a stack. If you need to manage asynchronous flow, use a queue. And if you want high performance, favor contiguous memory allocation to keep the CPU fed.